All right, thanks, Jeff. So yeah, Sean and I, we're we wanted to try to continue with discussion on flash flooding. If you remember when we first started these science sharings, or the SOO DOH call led by SOOs and DOHs, Steve Caton and I started out with a discussion on the use of flash in flash flood situations, but that was like, gosh, almost a year and a half ago now, if not longer. So we're now that we've done the full circle and everyone's had their turn, we're doing it again. So, but this time, instead of me yapping about it for an hour, I actually have the pleasure to introduce Steve Martinaitis from NSSL out in Norman. And he's going to talk about flash, actually. I met Steve a couple of years ago at the flash flood test bed out there, and we use flash a lot, in that. And I can truly say that, at least in Wakefield here, we are pretty much, flash is we're using flash every hydro event. I mean, really, we have it up constantly, even during just regular thunderstorms. I mean, it's so beneficial, and I would argue one of the better things for flash flooding, diagnosing flash flooding, and at least certainly the last few years, if not longer. So really beneficial. And Steve is going to talk a little bit about the use of it in urban areas specifically, which is, part of the Eastern Region AOP for this year of helping to better diagnose and message urban flash flooding. So without further ado, then I'll talk a little bit about what we're doing here, and then Sean will discuss, have a discussion on what RFC's support for flash flooding as well. So we should have a good show here today. So without further ado, I'll stop talking and let Steve have it. So thanks so much, Steve.
Yeah, you're welcome, and thank you. It's good to see a number of familiar names and faces again. I think it's been a while since I've had a chance to talk with some of you all, and so I'm gonna get my screen going here. So I've got two different monitors. So there's two other people I'd want to introduce. First is Jill Hardy. She is with the University of Oklahoma in Sims and with the Warning Decision Training Division. And her work is focused on training with heavy rainfall, flash flood type events. So she does a lot of training with flash, but she's also leading efforts with relating flash to impact-based warning tags. The other person I want to introduce is JJ Gurley. He is with the National Severe Storms Laboratory. He was the one who actually developed the flash system. And of course, I'm Steve. I'm also with OU Sims and NSSL, and I kind of fit in the middle between all this. I do a lot of the research to operations, work with it, as Mike mentioned, with the test bed. So both JJ and Jill are on the call. So if you have questions for any of us, please, feel free to ask. So Flash, just to give a quick background on how we got to this point, Flash was a project that started back in 2012 at NSSL. Is basically piggybacking on the success of MRMS, building off that infrastructure on its high spatial temporal resolution. Through this, we're the group there at NSSL under JJ's team developed such things as the EF5, which is this big ensemble framework bringing multiple hydrologic models into the system. CREST, which was helped develop with NASA, SAC SMA, which has been around for a few decades, and then a hydrophobic option, which basically turns all water into runoff. None of it gets infiltrated. On top of the hydrologic models, there are preset comparison tools comparing the MRMS radar-only QPEs to flash flood guidance developed at the RFCs and Mosaic at WPC, and then the average recurrent intervals from NOAA Atlas 14. All these products were tested in the HMT hydro experiment. The first running of it was from 2014 to 2016. And then after all the evaluations from it. It was eventually, transitioned into NWS operations in 2018. So from the analysis of the Flash products during the test bed, they were all done in real time. So we were highly dependent on weather occurring while we were running, which made it interesting for some of the leaner days where we didn't have too much action. But we had a fair number of events throughout the 3-year period that we initially ran. And one of the themes that came up during the testbed was how forecasters were documenting product performance during more urban events. So with the images on the screen here, we're focused on an event in Wichita, Kansas in 2015, where they had 2 to 3 inches of rain over a period of an hour, hour and a half. The flash flood guidance products really didn't have much of a signal, didn't reach that 100% threshold, and the return periods were more relatively common of what you would find, just 5 years, 2 to 5 years maybe. But the Crest unit streamflow product had a pretty pronounced signal over the urban area, with the blue being the urban boundary, and that's where the flash flood reports occurred, were where the flash unit streamflow signal was. So with stranded vehicles and flooded roads, and I believe a couple water rescues as well. So what makes Flash, and specifically the Crest model, different from other hydrologic modeling components and other products and tools that you might use in flash flood operations is the incorporation of an imperviousness field, and that's based on land use classifications. So a lot of different variables are brought into the model, but this is the key one that helps with identifying urban flash flooding. And with the map here, you can pretty much pick out your favorite metropolitan area: DFW, Denver, LA, Phoenix, Atlanta, New York, DC. They all stand out like a sore thumb with this map. And this is really what helps drive the model with getting that signal by not infiltrating as much water, allowing it to run off in these concrete jungles. So after the summer of 2019, our division chief, Alan Gerard, noted that there were a lot of high-level urban events over the summer. So we decided to do some analysis on them. So we analyzed both the MARFC QPEs and the various flash fields to find notable trends in the data. We stuck with 6 specific events. I actually highlighted 4 of them that occurred within Eastern region. So it was kind of a busy summer for you all there. All the analysis were focused on representative flash flood reports for each event, and on a 3x3 gridded averaging, so you didn't have to worry about the kind of the pixelated, noisy nature of each product. It all got smoothed out in the averaging to see how our products performed. So the first part of our analysis was the evaluations of the MARFC QP products. We actually did this with both the radar only based one that we had that was reflectivity only, which was operational at the time, and then our dual polarization QP. I'll just focus on the dual pol QP since this is now the operational product. All the events were synced together time-wise by using the onset of instantaneous rates of about a ½ inch an hour. So we set that as time t equals 0. As you notice, most of the significant rain rates occurred anywhere between t plus 0 time of t 0 minutes, actually more like t plus 4 minutes, all the way up to about t plus 50 minutes. So the greater rain rates all fell within about a 50-minute period for these events. Two of them, they had longer duration rainfalls, notably the Baltimore and the St. Louis events. And on average, over the 2-hour period from that, T equals 0 minutes time step, they averaged about 74 millimeters of rain for these events. To go into the precipitation analysis, the comparison tools within Flash, I'll start off with the flash flow guidance ratio. I will first note that this is the flash flow guidance that's generated by the RFCs and Mosaic by WPC. So it doesn't have any of the forced flash flow guidance that the local offices have. So they don't really account for so much things like urbanization and burn scars in there. So it's just based on the different soil temperature and water parameters. So just strictly using this, only one event, the DC event, which is, as you see, is going to be anomalous. This is kind of like the extreme event that we had for the 6 different cases. Only had the flash flood guidance ratio exceeded within 30 minutes of the onset of excessive rain rates. 4 of the events finally did exceed flash flood guidance ratio within 50 minutes of the onset of rainfall. And there was one event, the Richmond event, that really didn't exceed flash flood guidance for its representative report. So no, it really did just take a while for the rainfall rates to be reflected back in the flash flood guidance ratio. A similar trend when comparing it to the average recurrence interval. There were a wide array of values. Again, the DC event sticks out like a sore thumb with recurrence intervals up exceeding 150 years. But most of them were generally small. 3 of the 6 events had ARIs of less than 20 years. 2 of them, the Minneapolis and Newark events, had ARIs of under 2 years. So using that, it would have just been shown as a more common rainfall event, nothing that really stood out. You can see differences on when they peaked. Most of them peaked around T plus 60 or 70 minutes. Again, the Baltimore and St. Louis events ended up being more longer duration events, so you start seeing it reflected in other different recurrence intervals and then reflected back into the maximum value. So they were still going up at the end of our 2-hour analysis. And now to look at this with crest and the maximum unit stream flow. Instead of seeing the products reflecting a potential flash flood event 50, 60, 70 minutes after the rainfall started, most of them reached a threshold of at least 2 cubic meters per second per square kilometer within 30 minutes of the event. Some of them were reflecting it only 20 minutes after the onset of rainfall. Again, a variety of different levels were shown throughout the event, throughout these events, but all of them quickly exceeded the guidance level that we had of 2. Most of them peaked within 50 to 70 minutes of the event. The average value at this peak was 8 cubic meters per second per square kilometer. So not only were they peaking at the time where you were just seeing them start to reflect in things like flash flood guidance, they were peaking at pretty significant levels. To look at this from the perspective of when the first LSR occurred, first to note that the time of the first LSR generally occurred within 30 to 55 minutes of the event. So by the time you got that report in, we can see what the different flash products were looking like then. So starting with the flash flood guidance ratio, you note that half of the events did not exceed a ratio of 1 at the time of the first report. So if we use just strictly flash flood guidance, you could have potentially missed the event. With the average recurrence interval, that most of the events didn't really have a recurrence interval that really stood out. 3 of them were right around 2 years for the first LSR. And then for the crest unit streamflow, by the time that first report came out, all of them were at least above the guidance of 2 cubic meters per second per square kilometer. And then at the time of the report, some of them were at pretty high values of 8 to 10, signifying a significant event. And a lot of these were significant events. A lot of instances of flooded roads, stranded motorists, water rescues. A few of them had interstates that were closed. So there were high traffic areas that were impacted. I'll step through 2 events really quickly. This first one here is going to be from this study that we conducted at NSSL. So I chose the Richmond event. It was kind of representative of things that we were seeing throughout most of them. So this is one that was kind of a 1-2 punch for the area. So you had local convection forming ahead of an outflow boundary and then a boundary passing through the area. So you had this initial round of rainfall and then followed up with a secondary one. But really that first round was where these events occurred. So busy map, I know. So you have the instantaneous rainfall rates here with respect to time going from 040 UTC to 0130. So all this is in 10-minute intervals on June 1st, 2019. And then going through the unit streamflow values, the flash flood guidance ratio, and the ARIs, and all the different color scales are put below here. And then these dots here represent the LSRs when they're coming in during that 10-minute period. So as the event evolved, you can see you get more reports over the area, but there was already a signal within crest already in that 2 to 4 range for unit streamflow. But things like flash flood guidance ratio wasn't even really exceeding 0.5 or 0.6 for these events. And then the recurrence interval was generally in that 1 to 5 year period. There were areas that were showing higher values but didn't have the initial LSR reports in that area. But all in all, you can see that the crest products was the one that was really providing that initial signal and a little bit with the recurrence interval. But where the LSRs occurred was where flash was more pronounced. To go into something a little bit more recent, Henri was quite a notable event, given the rarity of landfalls up in the New England area. And plus, I just love tropical systems. I grew up in Florida. This is what I'm used to. So I focused on the events that occurred over Queens, Brooklyn, Manhattan, kind of this feature coming on shore over far western Long Island. So this was at 0Z on the 22nd of August. So we have the 1 hour radar only QP and then the different comparison products, flash flood guidance ratio here, the return interval, and then the crest unit streamflow. So as we step through it in time, we start seeing these higher accumulations shifting northward over Long Island. And the values here aren't too high. I mean, we're talking about 1/2 inch to maybe 1.25 inches. But because of how the crest model is built within flash and the imperviousness and accounting for the urbanization, the land use, you're already seeing a signal show up within the crest model, whereas you're not really seeing anything with recurrence interval. and then having the really low ratio values with comparing to flash flood guidance. So here it is, just 30 minutes later, this quick evolution of flash over the area. The New York City office had issued their flash flood warning at 0046, so this would have been the most recent flash data available for it. And then you can see how we evolved just over this 1 hour. You're starting to see more significant unit streamflow values generated with the runoff in the crest model. And I believe the first reports were coming in no more than an hour after this. So you get that that early signal within flash, you're able to warn on it and get lead time, which I believe the New York City office successfully did with over an hour of initial lead time for the first reports in Brooklyn and Queens. So this is what it looked like for an event just a few weeks ago, or last week, sorry. So we have all this knowledge with flash in urban areas, and now you at the Weather Service have been transitioning over to impact-based warnings, being able to communicate the potential severity of the event through predefined tags within WarnGen. So the question was, how can we relate flash with impact-based warnings? And that's where Jill comes in with her studies. So she organized a focus group with NWS forecasters and managers from 12 different offices across the country to explore how flash and MRMS products are correlated with flash flood reports and impact-based warning tags. So there was a series of goals within this focus group, with the end goal of creating best practices that could be leveraged throughout the entire Weather Service across different parts of the country and domains, and then produce training materials on it. So their first part was, when working with forecasters, was to collect what kind of local studies and guidance there is from different forecast offices, and they were able to get a lot of feedback on it, a lot of different examples of what to look for with different IBW guidelines, relating it back to flash, relating flash to different types of events, from nuisance events all the way up to significant and catastrophic events. So they were able to collect a lot of valuable feedback and guidance with it. And then from there, she was able to hold different meetings discussing all of this and trying to put all this together into more of a national set of guidelines. While this is all going on, there's other work being conducted, both locally, and then the example shown here was done at headquarters, was relating flash flood reports to the different IBW tags, so able to examine the reports, the wording within them, the kind of impacts that were, and then relate them to your base, considerable, and catastrophic tags that you would apply to the warning. So I'm going to get a visitor here. Oh, no. There you go. My little lap dog. So they were able to relate different things to different impacts to the tags. So looking at things just seeing standard standing water, simple road closures to base tags, and then going from things to debris flows, stranded vehicles, and a few water rescues considerable. It's all the way up to those extreme events, kind of like what we saw in Tennessee last week. So we have the work with the flash flood reports, and we have the work with comparing flash with IBW tags. So then she was able to help tie all this together and then use all the different studies to relate the reports and flash to the different tags. So this is a draft set of guidance that they are working on. It's still a work in progress. of looking at different CREST hydrologic model values for what can be related to to these tags. So then for you in the office, you don't have to sit there and potentially wait for reports to know if it is a considerable and catastrophic tag. You could potentially be a little bit more proactive in seeing maybe you're seeing a really high signal in flash. Maybe you could consider it consider maybe using a considerable tag for beforehand to get people to be a bit more proactive in taking action. The work that she's doing with this group is not just focusing on the hydrologic models. They have similar analysis for flash flow guidance ratios and for return intervals as well. So that's where we're at, to where we're going with all this. JJ and his group's been doing a lot of work with moving the flash products from deterministic to probabilistic. And that's something that we evaluated in a test bed in 2018 and 2019. Mike was a part of seeing those, initial projects. We were able to create various probabilistic products with this, just to give us the opportunity to evaluate different methodologies in creating probabilities, but also creating probabilistic products based on the potential severity of the event. So not only can you see the probability of a flash flood occurring, but the probability of it being a more moderate or major event. So the images shown on the screen here was just for a minor event in northern Kentucky. So you can see the various signals throughout the experimental probabilistic products. On the impact-based warning side, there is ongoing research on objectively matching the IBW tags with the flash products, both the deterministic ones, like I just highlighted earlier, but also with the probabilistic data as well. So hopefully in time, there could be probabilistic products that say probability of like base considerable or catastrophic flooding or something along the lines of that. I'm sure JJ can speak more to it. But other things that we have noted is that there's a lot of subjectivity in these flash flood reports, and then challenges in trying to classify them with the three tags, since there is some potential vagueness and ambiguity with it, where a report could fall under multiple categories. So there's emerging efforts going on trying to put more objectivity into flash flood reports. And one of those is the Flash Flood Severity Index. And that is led by Amanda Schroeder. She is the Senior Service Hydrologist at the Fort Worth office. So she's been working with other local offices and offices across Southern region, and also with headquarters on trying to create this index for flash flood reports so that you can eventually align reports with flash products and with IBW tags, so you have a cleaner, more objective look at tying all this together to know when to use these different tags. So that was all I have. I have our contact information there. We have different links to go to so you can view the products, the operational products online, the Flash webpage, and then the references there. The work related to comparing MRMS and Flash to the urban events of 2019 is in publication and is on early online release, plus some extra links here talking about Flash, the testbed experiment, and then other analysis of Flash with significant flash flood events. So thank you for your time and allowing me to speak to your group today.
Thank you so much, Steve. This was great and really excellent presentation and excellent review of some of the really excellent work that you all have been doing. And thanks to JJ and Jill for also being on the call too. I apologize. You should have introduced the two of you as well, but I really appreciate it. And yeah, I think the best way to go about this will be just if anyone has any questions, just raise your hand and I'll let you go. So Frank, you were first. I see Frank and Bob have raised your hands, but I'll let you go first, Frank, since you raised your hand first.
Okay, hopefully you don't hear the trash truck in my neighborhood in the background here, but the issue with we certainly use things like the ratios quite often in our office. The problem I have as a SOO is with the crest unit streamflow representation. As somebody who's colorblind, I can't make heads or tails about that. It's to me, it's a useless display. I'm not saying it's useless for everybody, but as me, colorblind, I just see noise, and that makes it impossible for me to train on too, because I can't see it. And so I'm wondering if there's any efforts at all to make this output available in, say, AHAP style or gauge style, where we can put in some specific predetermined points and use a time section to watch the value at those points, because that's something I could see and train on.
Okay, so I see. So you want it to look something like akin to a hydrograph, where you can watch the values.
Yeah, because I literally can't see any. It just looks like noise when I look at the unit crest information on the plan view. Just too many colors. It's not like an even pattern. It's scattered all about within that. And it's literally just noise to me.
Frank, there was some training recently on RGB color curves development for colorblind individuals in the Weather Service, and they came out and said basically 8% of the forecasters approximately have colorblind issues, and they were even a fairly detailed discussion. Maybe there could be some work developing an additional color curve that could help with that.
Yeah, I mean, you can work on some colors, but the problem is the noise of the data makes it almost impossible for any particular color scheme, because it's not simply what the color is, but it's the contrast and trying to focus on certain things. When it's as noisy as that data is to somebody who's colorblind, it makes it very hard to pick out what's important.
Right.
And a gauge history, if you will, crest history, or whatever you want to call it, that is something that's a whole lot easier to visualize and see impending problems.
The other thing I was going to mention is we just saw that you said that the display could be a smooth sum with a 3x3 smooth. That might be insightful to take a look at as well, besides just the pixelated product that we have now in AWIP. So I would like to see that. The other thing is you made reference to the impervious database for the land use. I would like to see the reference maps be available to the offices because I have questions, not just the city outlines of what we use now to designate urban and not urban. It would be nice to see if there's how much variance there is across an urban area, and we can examine other databases. I think that would be informative. The other question I have is right now the model is running every 10 minutes. There's approximately, almost a 16-minute lag when the data entering the system is stopped and we actually receive the output. I think it's somewhere like 15 minutes. I know in a perfect world, we'd like to have that more often, maybe have it run every 5 minutes. But it is a great system. The other thing I have here, question I have is the quantification of the flooding. And I think it looks as though some of the slides you showed with Jill's work, I'm on the MDP training initiative. Anyway, we're supposed to identify training gaps, and it looks as though we're heading toward quantifying flooding with flash, which sounds like a very good thing to do. And I guess ultimately, maybe when some of the training or conclusions are more firm or applicable to the nation, then there'll be training that's developed and disseminated. appears that we're on that. So I'll stop there.
Yeah, I want to briefly show, I don't want to take up, we're going to try to end by 11:30 today because of the Meg call, but I'm going to briefly show a little bit of what we've done here, just really brief though, here shortly. But one thing, Bob, the 3x3 filter, one thing that we've noticed in Wakefield is that sometimes those localized higher values actually do mean something. So then I do agree that we need to have I think it would be nice to sort of have some type of a smoothing, which I've actually tried on AWIPs, and it just I can get it to work, but it's super slow. But so it needs to be something that's done outside AWIPs. But anyhow, I agree that is nice for sort of a first order type look at Flash. I will say, but I can actually show you some examples to where some localized higher values actually it does actually mean something. Sometimes, especially in the urban areas, I've noticed that when you get really high values, there's sometimes, and even if it's only a couple pixels, we've noticed sometimes bad things really are happening. Worse than the standard, 2 inches of water on, going down Broad Street or something like that. So, while, I agree that I think a filter type thing is good. I think he still wants a native input. And last but not least, you're talking about it. So it's taking 16 minutes sometimes for your, to get in.
So if you get a run, let's say at 12:40, well, it'll show up 16 minutes after 12:40. And I'm waiting. There are times when you're waiting for every update.
I've noticed that it doesn't happen all the time here that late. It does happen sometimes. You're right. That's a processing issue. I think on probably the grip decoder that I think is more than unfortunately is sort of something we can't do much with, unfortunately. Because I do think it's pretty, the latency on the web page is pretty good though, right? It's less than that, I'm sure. That's why I keep this.
Yeah, well, the operational page, I believe, is pulling from NCO, so whatever the lag is at NCO is what we get there.
Right.
But we do run all this internally on our servers because our infrastructure was built to mimic that of NCO, which is why we're able to test things and have that easier transition over. The model, you should get that output within 6 to 8 minutes of valid time. I know that sometimes it has the appearance of being late, but I know other times there are data transmission issues where it actually is truly being late to the game. So that, that's unfortunate, and that's, hopefully something that is worked out with the communications issues with an NWS.
Yeah, I know, at least Bob, with my forecasters, they are ending up, they're looking at it on AWIPs, but quite frankly, they always have the operational product viewer up as well, simply because it does, a lot of times it does update a little bit faster than AWIPs. Is it ideal? No, but it is what it is, I guess. But so Mike and Bob, what you're saying, you're not the first to have mentioned it before. It's fortunately that's just out of our hands at NSSL. It's something that as data flow is upgraded within the weather service, hopefully that will become less of an issue. I just know that at NCO and things like the SBN are pretty well saturated, so there are at times, and that's just unfortunate. But circle back to everything. I know, Frank, that was a good suggestion.
Oh, I mean, we'll have to sit down and brainstorm how something that could be built. You know, the big thing's gonna be like how to AWIPs and work with the program office on that. But I like the idea. Other people like the idea too. So we made a note of it here, and we'll work on getting a reference map for imperviousness for review. So hopefully, Bob, Frank, that will.
Okay, thank you.
Awesome. Jeff, yeah, have your hand up.
Yeah, I guess a couple of things, man. First, the SBN team is very aware of some of the issues that have been experienced over the last several months with MRMS and flash latencies, and that is being investigated. There seems to be a couple of issues going on. Yeah, so there definitely are some problems at the SBN backup level. Some of them have been caused by other things going on, other data issues kind of clogging the pipe. But that gets rapidly reflected in data that updates every 2 minutes. In terms of, maybe a Frank, for your situation, have you tried the moving mediogram feature as maybe a short-term approach to interrogate the CREST streamflow data? I mean, I think there have been some other good suggestions here for longer term, like a flash flood prob severe kind of approach. But that might be something, at least that exists now, that might be worth experimenting with.
Yeah, the problem, and I will actually do that sometimes in certain cases. The problem, it becomes screen real estate.
Right.
That if that pops up, then you can't see your other stuff, and vice versa. So it really needs to be be able to show up in an editor or something within the D2D, rather than popping up a whole nother thing that blocks what you're trying to look at. It takes away from your situational awareness. Even something like, I think what Brian mentioned, the prob severe thing, where you've got it on a PC, or maybe it's something that could be fed into like a Firefox for your text window that you're not using graphics on, or something like that. Some kind of thing like that, where you could, let's say you've got 10 points in your CWA, are especially acceptable to urban flooding. Just got that up there like you kind of do in the HydroView, and you just watch it. And I think to me, it's a whole lot easier to see something like that than it is to look at that. Now, again, I understand it's a unique problem, so I'm not blaming the Flash folks or anything. You've done excellent work, but it is an issue out there, and I think it's something to be considered as this process moves forward.
Well, Frank, I know especially you've got a particular urban flash flood hotspot in there in Columbia, so I can certainly see the application there.
Yeah, and it's, I imagine that other people have hotspots in their areas as well, but we don't, for the most part, where our elevation change isn't particularly significant. So urban is, except in extreme events, our flash flood stats, and that's just what it is, because we don't get the heavy canyon flooding or anything like that, or even elevation flooding like a lot of you see in the Ohio Valley and the Appalachian. We just don't have that in our CWA. But as anybody knows, when you get a flash flood in your main city, that's all that talks about. So, it's obviously where our IDSS comes to play, and any tools we have to improve that are useful.
We're the same way, Frank. Here today. We have a little bit in the Piedmont, but for the most part, it's Richmond and Hampton Roads, so our urban areas. So,
and
when it happens, it happens bad. So,
and one final quick question. Really intrigued and excited by this linkage to the flash flood severity index and flash. I'm wondering if you started to think about it, and this is really in a facets domain, to take that one step further and maybe start looking at it also in a forecast type of environment, say applying CAM, maybe WAFs to that approach, so that you could actually look at model QPF, and that, okay, if you were to see that rainfall and those rainfall rates being forecast by the model, what would be the flash response, and that's the potential flash flood severity. I think that looking forward in a facets environment could really help span the messaging gap from the warning to the watch.
Yeah, so Jeff, as part of the test bed in 2018 and 2019, we did link Flash with the warn-on forecast system. In 18, we did it with just static cases and in a case review mode, just to get the idea of that concept could work. And then in 2019, we actually linked, we put the two together and actually ran them in a displaced real-time mode. The analysis for that is finished, just on the simple probabilistic flash and warn-on forecast coupling. I'm hoping I get that paper finished in the next month or two to submit to BAMS, so we can put it out there. But then, yeah, the next step would be, taking all of this and putting it together, because that coupling of flash and warn-on forecast to look at that, the future, short-term look of that 0 to 3 hours out using the ensemble QPFs was shown to improve lead time and situational awareness of events, and then coupling that information with IBW tags or FFSI, so you can get an idea of not just the potential for flash flooding, but then also having this predictive component of the type of severity you might see in the next few hours, is kind of hoping what we envision for flash flooding efforts within facets, as the facets concept continues to evolve and mature. So, and then that goes into, I guess, Steve Zubrick's question here about FFSI being a predictive index. So the way it was developed, it's the way the concept was developed for FFSI by Amanda and her co-authors was it to be initially done as like a post-event type of a tool, kind of like analyzing a tornado after a fact to assess all the reports and then assign a value to it. But once that database is built, then you can potentially link that to predictive tools like runoff from the flash crest model, or in the future having that coupled with warn-on forecast to make it more of a predictive type of tool. But its initial development is post-event.
Awesome. So I guess, does anyone else have, I don't see any hands up, I don't think, but does anyone else have any comments or questions? Oh, JJ, go for it. I saw you come. Yeah.
Yeah, I just wanted to respond to Jeff's question about moving into the QPF realm as forcing, and I kind of put that in as a comment earlier. And so, yeah, that's really the kind of the future, if not kind of the end goal for Flash, is to ultimately get it to that point. But before doing so, and we've got a web page where we use the HER and force it into Flash and have that on a web page kind of in the background. And I guess the caution in doing that is you produce a lot of precision in Flash, as you noted, and so if you're wrong in the spatial location of those objects, and you can have what appears to be a whole lot of confidence in the wrong answer, and water's rolling on the other side of the hill, and it can be kind of misleading. And so I think before we sort of turn that loose, we're working on a method that kind of accounts for those spatial uncertainties. And in order to do that, you have to be that you can't, if the QPF folks, NWP folks give me a 100-member ensemble, or even a 26-member, or even 10-member, then we can't run the hydrologic models that many times in parallel, because it's almost kind of a modern miracle that we can run it within 10 minutes at over 10 million grid points across the U.S. And it takes about 8 minutes to do that. If it took 2 minutes to do it, we'd run it every 2 minutes, but that's really all we can do at this point. So if I get too many scenarios, you can't just run it over and over again. The INSEP would not allow us to do that. So we're kind of maxed out on what we can do there. So we are working on a method that kind of borrows hydrographs, so to speak, and I'll be able to speak to that sometime in the future. But we're getting pretty close on getting that finalized, and also using nowcast. So we kind of want to work on this segue between QBE at analysis time to nowcast. Into the kind of 0 to 2 hour time frame, and then after that we use QPFs from warn and forecast systems. So that is kind of the eventual goal where we want to move pretty quickly. Also, there was a question about accounting for from Julia about lakes and things and retention ponds, and we've had this discussion before in the past, and it's a difficult problem to handle. It really is. I mean, we know where they are, but the issue is, do we just, zero out everything below them? And that could be dangerous too, because at some point they do fill, they do release, and then you have a human behind the wheel that's controlling some of this. And so I think we kind of took the attitude that most of our problems on flash flooding are usually upstream of those. And if you're dealing with the bigger rivers, I don't envy the folks in Alabama that have to deal with that, but they do, so they've got some techniques to address that. So I think the best way to handle it, I would hope within AWIPS or other tools that you have some ability to overlay them and just use a kind of human analysis to kind of make that decision, rather than having us try to design something that's not going to be very accurate in terms of quantifying the volume of these, and is it full, is it spilling, and a lot of considerations would need to be taken into account there. So, I think that kind of covers a few of the things. Let's see, Bob just said, can we run it every 5 minutes for just urban areas? Gosh. I guess the short answer would be that would be very difficult to do, in that it would be kind of disconnected from the urban areas. And the thing is, running the hydro model is that it has to be connected because of the routing. So the routing connects everything, from headwaters all the way to the mouth of the Mississippi into the Gulf, and so it would be challenging to do. I think. What would be better is if we could make an argument somehow to INSEP to get, or if things move to the cloud, for instance, and we got a little more horsepower, I think that would be the better approach. And maybe we could get it down to 6 minutes. I've seen great improvements by modeling at 250 meters, and we've had some projects in foreign countries and like Switzerland, and we were running there in complex terrain at 10 meters. And in the routing is really improved. Like I did see an instance with the recent event in Tennessee where they got the 17-incher, where we had a couple of grid points that were acting strangely because of the routing is pretty coarse at 1 kilometer. So I think a lot of things could be solved with just more horsepower and better resolution, rather than trying to do some tricks. And then the last thing that just came to mind, and then I'll shut up, would be the smoothing. And I think, and Mike said that, yeah, that's something that can be done with an AWIPS to bog it down a little bit. But I would be a little cautious in having us do that, because there are details, if you smooth and you can get rid of river. And I know if you go, like, we have to consider the folks out west, and routing is absolutely essential there. I mean, they get these little splats that then, you know, bleed out. And if you smooth that, you wouldn't see your streams anymore and your low water crossings. So anyhow, we appreciate your feedbacks, and definitely, you know, I think that's what made this whole project so, the utility was high just from the beginning, mainly because we had forecasters giving us feedbacks from the very beginning through all the testbed experiments and just forecaster involvement. And I think that's why it wasn't something that just kind of came tossed over the transom that you had to accept and figure out, but it's been really a dual feedback kind of process. So we appreciate that. And any more feedbacks or issues you have, like with the color tables, I think that's something that can be solved on a local AWIPS basis, I would think, with the customized color table. But anyhow, thanks for your feedbacks.
All right, thanks. Yeah, thanks, JJ. That's really, really good stuff. And I think with that, it's 11 o'clock. And so, and I know a lot of people want to get onto the MEG call at 11:30. So I think I will just go ahead and I'll forego my discussion point, my discussion slides. I guess the one thing I will really quick show everybody, let me, if I can present here really quick. But first of all, I want to really thank Steve and Jill and JJ for being on, and I'm sure they're great to work with, and they're always really prompt to respond to emails and whatnot. So you know, feel free to contact them with any questions you may have. So this was great. So thank you, everyone. You're certainly free to stay on as well. But one thing I wanted to share really quick was a couple things. You should be able to see. Yeah. So with regards to the research that we've done here locally, you know, we've done some similar things as a lot of other offices, you know, but we've actually have cataloged pretty much all the flash flood events in the Mid-Atlantic, and then actually gone in and categorized those with, you know, with regards to their, you know, base, considerable, catastrophic. And then we've actually looked at the crest unit streamflow values and sort of around that point. And we've done that to actually, you know, so because we know that there's errors in flash flood time reports, flash flood, you know, where they're actually located. It could be more than one point. So we've actually we actually have sort of smoothed out the data in a post-process sense, but not even post-process, just sort of, we've smoothed out the data in the analysis, I mean, and to actually look at the, you know, to analyze what values may occur in the crest unit streamflow for base, for considerable, so on and so forth. And this is what we came up with. This was just for 2018, but what I've done is sort of done a box and whiskers for urban areas and here, and then non-urban areas. And you can see they are fairly similar, but there are some important differences. For example, the non-urban areas are actually a little bit lower with their crest unit streamflow values compared to urban locations. And I don't know exactly why that could be. And maybe it's because there may be less initial runoff in the non-urban, you know, the rural areas. You know, so I don't know. There's some ideas of what could be going on, but the bottom line is that we're actually using these charts to actually sort of have almost our own local probability of when, you know, if there's, you know, maybe a considerable flash flood. And so what I've done is come up with some guidance values that Steve talked about. I shared these with folks out at NSSL and you know, Jill there. But you know, what we're looking at is basically once we get to even especially in urban areas, as low as 300 cubic meters, or I guess 300 CFS, sorry, you know, 300 CFS, we should start considering a considerable tag. And then when we get to 500, again, based on the unit stream, based on our box and whiskers, that's pretty much when we are going to be issuing a considerable, even if we're not seeing or not hearing about any flash flood reports yet. And that's from, we've done, again, a lot of analysis. And one example of this is actually this report, this event we had. Well, it's actually the same event that Steve talked about. But, in this event here, we had a lot of, 300 to 400 values here, but we did have some embedded values of higher, 600 to 1,000, and even one above 1,000 up here. And we had a lot of considerable reports in here, even though our ARI, our recurrence interval, wasn't that great, maybe 2 to 3 years. Our worst case flash flood, QP ratio wasn't that great, maybe up to 1, but not, it wasn't that great, put it that way. So, as Steve mentioned, but again, we had considerable flash flooding in these locations. And again, that was right where sort of the worst values of flash were also located as well. So with that being said, I don't want to take away from Seann's presentation. The only other thing I do want to show you is that I do actually have a bundle. I'll be happy to share it with you all that helps, at least for that we use here all the time, sort of this 6-panel that has sort of the kitchen sink, from the MRMS reflectivity to the QPE. And we are actually I'm actually producing a local 16-minute QPE, as well as a 3-hour QPE every 2 minutes, because the stuff we get over at SBN, doesn't, 3 hours actually only produced every hour. And we don't actually get the 15 minutes, or if we do, we don't always get it. So what I'm doing is actually just computing it based on the 1 hour. I'm just doing some subtraction and addition and stuff like that to get that. And it's actually very accurate. So I'll be happy to send that to you all as well. And then the rest of the stuff is just the standard products from the MRMS and the Flash. So with that being said, I think I will stop here and go over to Seann so he can do his talk here for the next half hour. So again, thanks again to Steve and JJ and Jill for being on. I really appreciate it. So with that, I will stop presenting, and Seann, you've got the floor. So.
Well, thanks a lot, Mike. Yeah, I really appreciate getting this chance here, and seeing what Steve had to present first. That really helps. Hopefully, it'll help me frame what I want to say and give you some better context. So here I'm going to start talking more about a little, bigger basins, longer lead times, and some of the things that we are able to do at the RFCs. These are tools that are mostly in the CHIPS environment. I think most of you are familiar with the CHIPS tool that we use at the RFC, at least in concept. And also, this is what I want to present today is just kind of some of the things that we have internally that we're starting to look at. We've been looking at maybe for a couple of years, and we use it to help do our own forecast, but it's not something that's usually published on the web or anything like that. But I do want to highlight the value it has, and then maybe stimulate some interest or some discussion and ideas on potentially improvements and things like that. Also, it's not something that's a long-term research project, but it is a culmination of the ability to leverage the Fuse technology that goes into chips. That's the Dutch software that provides the foundation for chips, and it does provide a lot of flexibility in how we can look at data and run multiple models and things like that. So when I say rapid onset, I don't know if there's a standard definition. What I'm talking about is anything where the time from base flow to where it reaches flood stage or higher is less than 24 hours, basically. So we're talking a little bit longer than, say, an urban flash flood lead time or time, scale of flood. And I'm limiting to, at least the analysis that I'm going to present, I'm limiting to basins where we actually do forecasts. We do have a lot of flashy headwaters in the middle Atlantic region, some of them where we offer forecasts. But there are four kind of things I thought would be interesting to share with the group, things that we're looking at now, and maybe some insights related to those items. The first one is, for the longest time, most offices, river forecast centers have been using 6-hour time step models. Now we're running a few more 1-hour time step models in our region anyway, and it's been useful, so I wanted to highlight some examples of that. I also wanted to talk about the fact that, we have the Ensemble Products standard production that goes on the web, the MMEFS, HEFS, but we also are looking at quite a few contingency runs using higher resolution information. And that's really valuable, and I'll give some examples of what that offers us as well. It kind of goes back to, just to highlight what we're doing here. JJ pointed out that they'd like to have more ensembles for the high-res flash stuff, but computationally it's expensive. Well, in our case, our models are very simple, much coarser resolution, so we can do these, lots of contingencies and ensembles in fairly short order. The third thing I'll mention is how we use some of the supplemental stream gauges. And then the last thing, I do have some information on our evaluation of the water model. I know that's certainly something that WFOs are also starting to look at, and we're trying to use it when we can. So I'm only going to have a couple slides on each of these topics, but the first one is the hourly time step modeling. This would be something more akin to site-specific, which I know the WFOs, some of the WFOs have run locally. But these are 18 basins that we've implemented these hourly models internally in our chip system. And we just run them in parallel to our 6-hour models so that when we do have a flashy event, we have the opportunity to update the model a little more frequently. And then we can also simulate using the HER as a forecast forcing. But because it's in the normal modeling framework that we use, if we don't think if we think the HER is running too hot or something, we can always make some adjustments to that forecast and see what that contingency would give us. So again, I'm going to have a few slides at the end to show some case studies with using the 1-hour model and where it's been beneficial. But before I get to that, I wanted to talk about the other types of contingencies that we run, not just in these 18 basins, but for all of our forecast basins. So in addition to the HEFS and MMEFS, internally we run the PQPF fields through all of our basins and generate the forecasts associated with that. One of the great aspects of the PQPF, it does give you information from a broader range of models. They use, I can't remember the number now, but I think it's in excess of 40 different ensemble members to produce PQPF. And so we can take the 5%, the rainfall amounts with a 5% chance of exceeding a certain amount and run those through the model. And we can get worst case scenario. It's not really applicable to large watersheds, but when we're looking just at headwaters, I think it is kind of a relevant source of information. So that is something that we can look at internally. And when we're in a situation where we think there's going to be potential for flash flooding or rapid response flooding later in the day, we may look at those early in the morning, particularly in the convective season, to kind of get an early idea of the risk. Let's see. So I heard a beep, but I don't have the display up. So I think I'll see if there's questions at the end. So please hold that thought. Another thing that we run through our models is not just the HER, as I mentioned, for those headwaters, but we'll run it for every hour. And so we can look at these plots where we have the last 4 HER runs or something. And certainly that's useful because you can see if the storm is evolving throughout the day. Is it still hitting the same basin over and over, or is it moving around, or is the intensity changing? So that's another tool that we use quite often in the convective season. And the next slide I have is just an example where we're plotting up the HER, which is what we use for our RFC forecast in this particular event, which is a headwater in Virginia, and compare that to the latest available runs from like the Jeffs and ACE, and we even run through the the deterministic precip from ECMWF, deterministic GFS, and NBM, in addition to our our standard RFC QPF that we generate as our basic deterministic approach. And you can see in this case just the latency and the resolution. Clearly, there was a signal from the HER run that there might be flooding here. The other ones just didn't update us quick enough, or we didn't have a recent update, or just the resolution didn't capture that intense rain. So these are just some things that we can do now we couldn't do a couple years ago in terms of looking at the impacts of say a high resolution forecast. So the next thing I wanted to just highlight is we do, at least in our region of the country, and I think it's true for probably most of the eastern U.S., there are a lot of stream gauges that we don't actually issue forecasts. Some of these are upstream of our forecast points, and so for flashy events, and I know we communicate about this with the WFOs sometimes. We say, hey, we see the upstream gauges doing something. How do we think that's going to impact our forecast point? But here you can see that there's really a lot of gauges that we can leverage in kind of qualitatively assisting with our forecasting. And I'll talk about also looking at the water model performance at some of these gauges in a few minutes. But one of the really simple things, old school hydrology here, for a few of these places, we can develop these relationships between what we call the supplemental gauges, the interior gauges, and the outlet points. So here's a watershed in New Jersey. It's a headwater on the Millstone River. It's about 260 miles squared. And then we have this other Griggstown gauge, which is just a bit upstream, smaller drainage area. And then we have a historical relationship between what's happening at Griggstown, what's happening at Blackwell's Mills. So that can be pretty useful at times to get a little confidence and potentially some lead time compared to what we get with our deterministic model runs, at least to support what we're seeing with our model runs. This is actually some screenshots from Henri earlier this week or over the weekend. And the Griggstown gauge, it was showing, on the evening of the event, basically August 22nd, it was showing that there was going to be it was already, rising to a 12.7 foot level, which would predict flooding at Blackwell's Mills. So even if we didn't have any modeling at all, and we just had this gauge, that would have given us 4 hour lead time saying, hey, it's Griggstown has risen. Now we know Blackwell Mills is probably going to hit flood stage. And also then later in the event, Griggstown started leveling off. That would have predicted something like 13.5 feet at the downstream location based on this relationship. And the actual crest ended up being 14.2 feet. We have a hydro model for Blackwell's Mills, and it was pretty consistent with this relationship for this event. But it does provide us with that additional confidence that we know we can go with a higher forecast because we see what's happening at Griggstown. So I just wanted to mention those supplemental points because I think they're pretty valuable, and we can also start looking at them in the context of the water model. We're starting to do that, but not. That's still an evolving learning curve. Anyway, so for the water model, we have, I think most people are probably familiar with WaterView. I know it's been used both at the RFCs, WFOs, and there's been a lot of good briefings from the Water Center. It's very good for situational awareness, understanding kind of what's coming down the pipe at the regional scale, maybe a watch time frame. But one of the things we want to know and understand is if we ingest these forecasts for particular points, or RFC points, or site-specific points, that might be these supplemental gauges. Is that really going to help our forecasts? Is there too much noise? Are they accurate? So one thing that we can do, ever since the water model first started getting run, the Water Center did provide these net CDF files on nomads that contained just the time series that we're interested in, the time series at our forecast points, the time series at the supplemental gauges. And those are pretty easy to ingest in our forecast system and then look at side by side with our forecasts. So I just have a few example events where we've done that. And then I also have some statistics for the water model evaluation. But here's an example. Earlier this year, in June, there was a heavy rainfall event that was just centered right over the Chadds Ford Basin, which is southeast of Philly, or southwest of Philly. This is a nice basin as far as gauging. Look at all those, interior gauges. Two of them that I'll have in my plots are the Modena and Downingtown gauge, which cover a decent chunk of the basin. So if you get a signal at those locations, you're expecting to have something downstream as well. So I'll just show the hydrographs here. I wanted to contrast. This is actually our 1 hour lumped model for that outlet point, the Chadds Ford forecast point. And then I just wanted to contrast what are the pros and cons of looking at the 1 hour lumped versus what we can get from the water model. And here we've got, the red dots, those are the observations. And the vertical black line is kind of the forecast T0. So technically, these plots are showing observed data that we wouldn't have had at the time. But I include that, of course, so we can see what actually happened. So the blue line in the upper plot is with the dots is our 6 hour lumped model. And that would have been what the model was showing at 18Z. And there was only about ½ inch of QPF at that time. So in that case, it wasn't really showing much. It wasn't showing that we were expecting minor flooding even in Chadds Ford. But if you had that extra time resolution, for this flashier headwater, and you reran the model at 20Z with a 1 hour lead time step in the bottom plot here, then you would get a signal for minor flooding. And that's what we can see now. We can run the model every hour, or once you start getting some heavy rain, and you can get a little bit quicker heads up for these headwaters. And then if you wait 4 more hours, you'll have the full data set for the 6 hour model run. And in that case, we also would have predicted a flood at the 0Z, and that would have also given some lead time, but you can add lead time in this case with the with the 1 hour simulation. So let's see what the water model did for this particular event. Again, this is for the same basin, and then the T0 is the black line, and these are just water model traces that we ingest into our system and plot next to the observations. And the black line is the outlet point, the Chadds Ford forecast. And the purple and green are the interior gauges where we have where the water model produces forecasts. And so in this case, if you recall the last slide, it was 20Z where the 1 hour model was starting to show potential for flooding. Here we have potential for the 19Z water model run. And then we look at, say, 2 hours later at the water model. Here you see a symptom of something that we do have, we do see quite often with the water model. It's pretty sensitive to additional rain. So you get some additional rain, and it's over predicting, fairly substantially here in this example, showing about 2 foot too high and 6 hours early in terms of this particular event and forecast. But so we look at the water model and we take it right now with a grain of salt in terms of how much we can look at it quantitatively. But we're gathering more data and more examples and improving our understanding of when it's when it can be used. I have another case. I'll show the same type of plots. This is a basin in New Jersey, and this is from Henri again earlier this week. This is a pretty small basin for us, anyways. It's 55 miles squared. And then the two plots here are for 22Z forecasts. The upper left is the 1 hour model, and that's just essentially the model without any modifications. And the blue dots show pretty good correspondence with the observations, at least getting the rise approximate, not all the way to the crest that was observed later. And one thing that we can do, though, with the 1 hour model that we have in our system is we can see, okay, earlier on in the event, we're not matching that rate of that rise. So we might put a mod in. We might say, oh, we think the rainfall is a little bit underestimated. So we multiply it by 1.2 of what's observed. Or we might adjust the unit hydrograph if the pattern of the rainfall is not uniform in the basin. And that might capture that rise a little bit better. If we did that, that's what I'm showing in the lower right. And that would have been a really good forecast. And I think, I didn't actually go back and look at what our forecast was, but I'm pretty sure, we got this one reasonably well. It ended up being a moderate flood in the, earlier this week. So let's look at the water model. Again, if you look at 22Z, the water model was not quite as bullish on flooding in this basin as maybe what our model was. So it might not have given quite as much lead time. But then when you see 23Z, 0Z, 1Z, the black line here is the forecast at the outlet. You definitely see it was giving a signal of probably moderate flood or minor flooding. And then at the end, when you had all the observed rain come in, it actually was a little bit too high. But this is one case where the water model short range forecast was better than we usually see, I would say. So if we did have a record of confidence in this particular basin, it might have been, it might have helped us. And then you can see also on this plot, the green and orange, those are interior gauges where there is also a forecast. I guess I didn't plot early enough to see if those had captured the rise at the interior locations accurately or not. So that's an area for further evaluation over time. Okay, so now I'm going to step back a little bit. Those are just case studies. It's hard to really draw a lot of conclusion because you can kind of pick and choose your examples there. But here I'll step back and share at least some results from a broader verification work. And here I'm only, those examples I just showed were short range forecasts from the water model. So that's where the water model is driven by the HER. The verification I've got so far is only for medium range, where the water model is driven by GFS. And here I'm just comparing those medium range forecasts to RFC forecasts for day one. So it's the 24-hour lead time forecast observation pairs. And this is for almost a 2-year period, I think it's about 20 months or so, July 2019 to March 2021, where we've got an actual archive of the forecasts. The challenge is that this is National Water Model version 2.0, and now we're running 2.1. So, they changed the version. I don't know how much that really impacts the accuracy. Obviously, they're improving in a general sense broadly across the country from 2.0 to 2.1 to 3.0. But, the jury is still out on whether it would really impact these statistics a lot. But right now, the bottom line is we still are not seeing, a huge advantage with the water model at most of our locations. In fact, the bottom right here shows for either pairs that are above action or above minor flooding, where we match the forecast and observations. So this is showing the percent drop in RMSE when you go from looking at the water model to looking at our forecast for day one forecasts. So basically, the error decreases quite a bit, the root mean squared error, when you use our lumped model forecast compared to the medium range water model. And I'm only including basins here with a decent number of samples over this short 2-year period. There are a couple basins where the water model did well. There's one in Pennsylvania, or actually there's 2 in Pennsylvania. So those are basins where we may focus a little more on the water model, moving forward. But we're also working with the Water Center on, looking at how they do the calibration, understanding, what are some of the reasons for the differences. So kind of going back to the question I posed earlier, can we actually use this to improve our point forecasts or site-specific forecasts? Probably not yet. I think it does provide an early heads up on some potential rises, but overall, we can't get the accuracy that we want. Over the past couple of years when we've been looking at the results, the performance is quite variable. Doesn't give us a lot of confidence, but there are some basins we might want to start looking at now that we've got some statistics. And it's ongoing. We want to do a lot more. There are limitations. The Water Center is certainly going to keep working on the model structure and the calibration. You can't do state updating, which is something that really benefits us when we get those fast rising basins. We can make some updates and tune our forecast a bit. Doesn't give us a lot more lead time, but we can probably improve the accuracy. And then again, we can't do all these contingencies with the water model that we can do, like multiple HER runs or ensembles with PQPF or those types of things. So there are limitations, but certainly the wave of the future, I guess. So future plans. I talked about the hourly models. That's a decent amount of work to add those at the RFC. So we may add a few more, but probably not a lot. That's where we hope the water model can help us out in the future. The water model evaluations, the statistics I showed is pretty limited. We could expand that to short range forecasts, to supplemental locations, hopefully gain some more insights, and see, again, where we can leverage it. Some of those displays I showed with the multiple traces can be enhanced. I'd definitely like to look at href, running that through the models. href has the limitation, it's only run a couple times a day, so it doesn't give you as much value in terms of latency. And then the last thing I just put on here is we are getting an enhanced archiving capability, which is going to make it a lot easier to go back and look at these events like I've been showing. To do the plots I've been showing here, it kind of required manually going in and getting the information out or copying over an old database, and it takes quite a bit of time. So those are some things we're working on, and I don't like having this presentation, so I can't see you folks. So I'm going to shrink back down, and hopefully there'll be a few minutes for questions. And hopefully I got through that to where it was clear. So are there any questions at this point? Hands raised. Brian, go ahead.
Hey, Sean. Yeah, I just got to say great job with the forecast for Henry. I'm at Mount Holly. Great job. You guys did a bang-up job. That's all I have. Thank you.
I appreciate that. Yeah, I realize, what I'm presenting, is a little bit more out of the box for you guys because you can't see it in your own office. But I did want to share it so that, if you see things that we're looking at that you didn't know about, you can certainly follow up and ask. What about other things right now? Go ahead, Mike.
Hey, Sean. Just a quick question. And maybe this is for you and for even the Flash folks. But there's the unit stream flow, but then there's also the stream flow, output. And I guess have you looked at that at all? Like tried to verify that? I mean, I know the national water model is the sort of the future, but at least in an event, we had an event a couple of years ago that there was all kinds of flash flooding up in Charlottesville, but the water was routed down, to Palmyra and along the Rivanna River, and looking at the water model actually didn't. I mean, it's helped some, but wasn't terribly accurate. But the looking at the flash streamflow data actually did provide some help, and we've seen that also in some of our other smaller stem rivers, outside of the sort of the RFC, away from forecast points from the RFC. But have you looked at that at all?
Well, I don't know. I mean, if the question is more like if we looked at time series output from Flash, the answer is no, not really.
I was just curious.
But yeah, I mean, it hasn't been as accessible, I guess, and
yeah, okay.
And I think, but the unit streamflow question.
Well, this is actually streamflow. It's actually not the unit stream. It's actually the streamflow.
Yeah. No.
Okay. I was just curious.
But I do think, I mean, it's an interesting, I don't know if you'd call it a paradigm shift or just an interesting challenge. As you move to smaller and smaller scales, you start thinking, well, how accurate do I really need to be? Because I don't necessarily have observations of the actual flow, but I do know that there was damage or there was, a problem. And so if I can just get, okay, this is a 1 in 20 year event, then that's valuable information. You don't have to have the exact flow. And that's one of the main concepts behind Flash. And I think it's a great approach. So JJ, go ahead.
Yeah, I think Sean captured it. I don't envy the water center having to go against models with a lot of calibration, and how do you calibrate a gridded model at every grid point? I think is a big challenge. So, but I wanted to raise a point because I think that Jim Noel is on here, and that we had some email discussion, and I actually had to ask my boss Alan Gerard when he what SSHP meant. So I understand this is a hydrologic program, maybe a model that's kind of intended to be used in kind of a time series fashion at ungauged grid cells. Am I capturing that right?
JJ, you are.
Yeah, I would just add that typically the applications are at gauge locations as opposed to ungauged, but it's definitely small streams. And I don't know if Jim wants to add anything else, but yes.
No, I think that's good.
All right. Are there any other questions for Sean or JJ or Steve or Jill or myself or anyone? Going once, going twice. All right. Yeah. Yes, you have anything?
Yeah. All right. Before everybody goes, Eric and Jordan have a quick announcement.
Yeah, hey everyone. We just wanted to remind everyone that on Wednesday, September 15th, there's going to be a town hall with the MDL total water level folks, Arthur Taylor, Yujing Li. So just it's going to be from 10 a.m. to noon. The discussions will be on the ETSS, PETS, P-Surge models. Really hoping to have that as an open discussion back and forth. And it's really going to just be a time to ask the developers questions and try and learn about what they've done in the recent updates, because those models have been updated recently, and just have a good learning experience. We can pass some operational questions to them, and they can tell us some things too. So just to keep that on your schedule, and we'll probably be sending an email out again reminding probably Monday for everybody.
I'll just also add in the Eastern Region calendar right now, it is up there in the information that you can get some background ahead of that conversation is included in that link, and everything else Eric said, I second. Good there.
All right, thanks everyone. And again, our next SOO DOH call, SSD led, will be on September 9th. Enjoy the rest of your day, everyone.